a subset. Well, yeah, of course every member is a subset. Because the members of this thing are these two things, and they actually are subsets. The empty set is subset. This is a subset as well. And it follows from these properties. Why? Well, because every member of the original thing is a subset. Okay. Let's see. Here's another thing that we might notice. Suppose you have a whole set of ordinals. Suppose big A is a set of ordinals. Well, it's easy to verify. Here's another way you can get a new ordinal. You give me a bunch of different ordinals, like, how about this one? This one and this one, 1 and 2. Here's a set of ordinals. Or here's another set, 0, 1, and 3. That's a set, yes? Well, one thing I could do to create another ordinal is to take their union. And we have a special name for their union. We call it sup of A. It's defined to be their union of A. I won't go into what sup means because you already have seen something like this before. We can think of this as a kind of supremum. What's it doing? It's taking the union of these things. It's an ordinal. Ah, interesting. Okay, so what does this mean? Are there any other ordinals besides the obvious ones? Well, yeah. So let's see. So this is I should just say what von Neumann's theorem here is. So it turns out you give me any well-ordered set, I claim any well-ordered set is actually order isomorphic to one of these, to some ordinal alpha. So sorry, that's to be more precise, to some ordinal. Like, for instance, this thing. It's order isomorphic to the successor of 3. This thing is order isomorphic to, well, I haven't given it a name, but how would you define this in terms of things you might already know? The sup of all the finite ordinals, right? It would be the sup of 1, union 2, union 3, union 4, union 5, that construction. Okay, we actually do have a name for that. It goes something like this. Let's see, if I could order the ordinals. 0, 1, 2, 3, 4. Okay, starting there. I'll just keep going, yeah? And each time I'm taking a successor, aren't I, right? But you could imagine then, okay, finish taking all those successors. That gives you a set of ordinals. But now you can do a new operation, which would be take the sup, right? That sup is the order type of the natural numbers. And so we have a name for that ordinal, the one that lives after all of these. After all of these, we give it a name. We call it omega. Okay? So it's the first infinite ordinal. It's countable. Okay? It's not finite, and it's clearly, you can, every element in it can be put in bijection with the natural numbers. Okay? The other thing I want you to notice is it's the first example of something That's, well, okay. Except for 0, it's the first example of something that's not a successor of anything. It's given by the supremum construction, so it has a special name. We call it a limit ordinal. A limit ordinal is not the successor. Is not S of alpha for any alpha. It's not a successor ordinal. Okay. Oh, okay. Okay, well, let's see. What happens after you get to omega? Well, the next ordinal is... Yeah, that's a good name. When you throw in an extra point, that's called omega plus 1. What is omega plus 1 really? It's, yes, a successor of omega. It's actually also the supremum of all the things preceding it. Okay, Willie?
I'm wondering why omega is not order isomorphic to omega plus 1.
Oh, it's not order isomorphic? Because the picture of omega is like this. And we think of the next thing as the union of all the things previous to it. And the picture of omega plus 1 is this thing with one more thing.
I guess my question is, if they're both just countable, then they have the same cardinality. So it's hard for me to intuit how they can differ.
Yes, they have the same cardinality, but they're not the same ordinals, because the ordinals have an order. When you talk about cardinality, all you're interested in is their bijection. But for order order types, you're interested in also preserving order. So there is no way you're going to make a bijection between these that'll preserve the order. Right? So tell me where you're going to send. I mean, where are you going to send this point? Well, it has to be bigger than everything else. Yes. So you better send it to something that's bigger than everything else. So this point, if there were such an order isomorphism, this point would have to go here. But then where does this point have to go? The next one down or something, right? But wherever this gets sent, you'll miss some, and then you're in trouble. Okay? Not the same order type. Great question. Okay, but, we can keep going. So the next ordinal after that we'll call omega plus 2, which is basically this picture with another dot. Yes? Omega plus 3, omega plus 4, ... And then... Yeah, what do you think we call this thing with the white and the green points? Yeah, actually, for various reasons, we don't call it that. We call it omega times 2. Because it's omega, if you like, we write omega plus omega, and we write omega times 2. It means do omega order type first, and then do another omega. Okay? This is not the same as 2 omega, which would be omega many 2's. So omega many 2's would be do 2, and then do 2, and then do 2. Yes? Whereas omega times 2 is do omega, and then do omega. Yes? How they're not order isomorphic? What do you think 2 times omega is an order isomorphic to? Look, I've got a bunch of points here, a bunch of points here, a bunch of points here. They're not order isomorphic because the limit ordinals, there are 2 of them here. Where are you going to send this limit ordinal, this one? Well, if you send it anywhere in this construction, there's only finitely many before. Whereas in this construction, there are infinitely many before. Okay? So in fact, 2 omega, believe it or not, is actually equal to omega in ordinal arithmetic. Okay? But it's not the same as omega times 2. Okay? So 2 omega, omega 2. So in ordinal arithmetic, multiplication